Lesson 6.1, Operations on Functions. So we are in Module 6, which has to do with inverse functions and radical functions. Oops, that's right here at the bottom of the page. Okay. And first, we're going to start with some basic operations. So right on the front page of this lesson, they have addition, subtraction, multiplication, and division, which you guys could probably figure out how to do that anyway. So if you're just adding two functions together or something like that. But see, if I flip ahead a couple of pages, they get into an interesting concept that's probably new for a lot of you guys. Is what if you have a function of a function, like f of g of x, or the other way, g of f of x? What if you embed a function inside a function? Right, what does that mean? How do you work with that? And what are some real life examples? All right, so we're going to see all of that here. So I'll take you guys through the book examples and then the puzzles that I have highlighted from the main section. So let's jump into all of that. Right, so first, they give you an f of x and a g of x. So these could be two different functions. And these very simply add and subtract them. Right, so f of x is, suppose it's negative x squared plus 3x plus 1. And then g of x, they're given as 2x squared minus 5. Right, like that. So there's your f of x, there's your g of x. Okay. Now, if you add those up, plus, that'd be f of x plus g of x. Well, all you have to do is combine like terms. I got 2x squared here, I have negative x squared here. Altogether, that gives me x squared. I have one x term, that's my 3x, so that'll just be there. Okay. And then 1 plus negative 5, that's like negative 4. That's it. That's the answer. Boom, done. Now, if you want to do f of x minus g of x, then you have to do this function minus this function. So negative x squared minus 2x squared, that's negative 3x squared. 3x minus 0, so I still got a 3x. Okay. Now, 1 minus negative 5, that's the same thing as 1 plus 5, or 6. Because subtracting negative, that's like adding a positive. So there's the sum, there's the difference of two functions. All right, boom, that's not too bad, right? Next, let's multiply and divide functions. And for example, 2, well, they change out the functions. All right. So I'll just follow what they have. So suppose we have a new f of x and a new g of x. Okay, f of x is 4x squared minus 2x plus 3. And g of x is negative x plus 5. So if I want to do f of x multiplied by g of x, by the way, the notation for that, sometimes you see this, it's f dot g, right? Like you're multiplying right, of x. Okay, so this is notation for multiplying the two functions together. It's really just what's going on. Well, let's see, I could do this one. So f of x is, of course, 4x squared minus 2x plus 3. I'm just copy pasting it from right here. Okay. And then my g of x, I'm multiplying right here, negative x plus 5. Okay. So I have three terms multiplied by two terms. I have to do a super distribution here. So this times this times this, and this, and this, and then this, and this. Boom, boom. Like that. All right, so let's put it all together. So f of x times g of x. Also called again f times g of x. There. We got 4x squared times negative x. That's negative 4x to the 3. Then 4x squared times 5, that's plus 20x squared. All right, and then next term. So these two guys, that's negative 2x. Actually, that's positive. Negative, negative makes it positive. That's positive 2x squared. And then next, that'd be negative 10x. All right, and then move on. Faster. Got negative 3x right there. And finally, 3 times 5 plus 15. Okay, so I have 1, 2, 3, 4, 5, 6 terms, but I think I could still clean this up a bit because I have my x squared terms here. These two can go together. And I have a couple of x terms right here. Those can go together. So put it all together. F of x times g of x is, okay, I got negative 4x to the 3. I have 22x squared. I have negative 13x, and I have a 15 tagged on the end. All right, so that should be that right there. Okay. What if I want to do f of x divided by g of x? You might see it written this way. F over g of x, which is the same thing as f of x over g of x. I think it makes more sense to write it out that way. Okay. Well, that would just got 4x squared minus 2x plus 3, all divided by negative x plus 5. Right. Now, a lot of times when I see something like this, I say, ooh, I wonder if I can factor apart that numerator. And a lot of times these are set up in such a way that it'll actually cancel out with the denominator. Uh, this one I don't think actually works like that. So if you try to factor the numerator, it doesn't factor nicely. Okay, so I'm just going to leave it like this. Okay. Now there is one more condition, actually your book right here. X cannot equal what? So there's one more condition. X cannot equal, well, and the rule is you're not allowed to divide by 0. So 5, right? X cannot be 5, because if you plug in 5, you would be divided by 0, right? Which would give you a vertical asymptote, right? Or if you could cancel out with the numerator, it would still be a whole, so it still wouldn't be part of the graph. So that's another condition. All right, so there you go. There's multiplication and division. Back here we did addition and subtraction. Okay. All right. And then, well, they do have a couple of real world examples here. So here, let's knock out both of those. Example 3. So we're just sticking with addition and subtraction here. We got the population of India as a function of time. So say pop of India, they're calling f of t, where t is the amount of time passed there. So that's 15.7 t plus 344.2. Okay? So t is the number of years after 1955. So 1955 is the base year, or year 0. Okay? And these are in millions of people. So if you plug in 0 for t, that would bring you back to the year 1955. You say India had 344 million people then. Right? Furthermore, it looks like every passing year, they're adding 15.7 million people. Now, this might not be exact, but this is kind of like an average over a couple of decades or something like that. Right? Your book also gives you population of USA, and we're going to call this G of T, so the population of the states. And that's 2.6 T plus 165.8. That means in year 0, which again corresponds to 1955, the population of the United States is about 165 billion. And then every year after that, we're adding on about 2.6 million. Just like that. Okay. The question here is, what function would represent how much greater is India's population compared to the United States any given year after 1955, right? Which is the difference. So the difference in population is the same thing as f of t minus g of t. So we're just going to subtract. So how much more populous is India than the States in any given year? Suppose like 1968 or whatever year you want to like. So I'm just doing the difference of these two. So 15 minus 2 is 13 t plus, okay. And then what's 344 t minus 165 8? It's 178.4. Okay. Yeah, these are millions of people. So if you want to say the year 1968, from 1955, that'll be 13 years after the base year. So you can plug in 13 for t. Okay. Uh, Now, India is growing faster than the States. How much? Oh, by 13 million more people. Okay. Every passing year. Right? So times however many years passed, and the initial gap that India had at the start was 178 million. And that was the initial gap. And so it's all there, all there. Ooh, an engaged couple wants to know what their combined income will be. We've got Casey's income. Here, let's do Casey as a function of time is 32,000 T. Okay. T is the number of years after marriage. Okay, so I think basically the income is $32,000. Right now that's every year. So if you're constantly working this job, you're picking up $32,000 per year. Okay? And Sam's is 30,000. And so Sam is a function of time. It's 30,000 per year, and then times number of years passed. That's like the total income acquired. Okay? So if you want to know what's the combined income, that'd be Casey plus Sam. All you have to do is add these together. So that'd be 62,000. Right, so they're collectively making 62,000 per year, and then times the number of years that passed represents how much altogether. That's all. Cool. Just add them together. Right. Okay, now we're finally getting to composite functions. Right, so I think this is probably new for most of you guys. It's like, what if you have a function within a function? A lot of times you'll see it written this way, like f of g of x. You guys see that open circle right there? A lot of times I hear it's pronounced like fog or actually. That's f of, not f of x, but f of g of x. So we're going to take the whole function g of x and plug it in where the x would go for f. Okay? Or you might see it the other way around. And this might be called goff. Okay? Again, this is not multiplying functions. This is putting a function inside another function. So this would be g of f of x. Okay? And usually these work out to be different outcomes. Right? There's exceptions to that, but that'll show up in the future. Okay? So your book actually starts just really basic with a table of values. Right? So they give you x and f of x, and then x and g of x. Right? These give you different values. So here, I'll do just a couple of these with you guys. Okay. So for example, what is about wait, let's wait a minute. About uh f of g of four. Right. Makes sense, right? F of g of four, right? Well, what is g of four? Well, if x is four, g of four is one. So this is the same thing as f of, and then g of four, I can plug in the y value of g, which is one, like that. Okay, so what is f of 1? Well, it says it right here. If x is 1, then f of x is 12, so the answer is 12. Okay, that's all. Okay. Let's do another one. How about down here? What if we're doing g of f of about 10? Let's try that. Okay, so what is f of 10? F of 10 is right here, right? Is 11. Right? If you plug in 10 for x, f of x is 11. That's like the y value. Right? Right, so we're taking our whole y value, we're plugging that in. That's the new x value of g, sort of, right? Yeah. And what is g of 11? G, it did, is that right? X. Did they not give that? G of 11. They did not. Oops. Okay. Well, okay, that's as best as I can do then. I was trying to shop it off the table. Let me find one that actually does work. G of, okay, this one should work, right? So what is G of f of 1? Let's try that. Okay. So that's G of, well, what is f of 1? F of 1 is right here. It's 12. You plug in 1 for x in your f of x, so you get 12. Okay. So we're looking for G of 12. What is G of 12? Okay, now G of 12 we do have. It's right here. So if you plug in 12 into G of x, you get 10. So the answer is 10. All right, so that one worked. All right. All right, there's that. Okay, now that's specific coordinates. What you'll tend to more often see is to plug a whole function into another function. So that brings us to example 5. Okay, now things get more exciting. They're giving us f of x is 2x minus 5, and g of x is 3x. All right, so that's the starting premise right there. They want you to find what's f of g of x and what's g of f of x, right? And also state the domain and range for each. So let's start with f of g. So f of g of x, or how I might prefer to think of it as f of g of x like this. It's the same thing, just weird notation. Right? Okay, we're going to take f of something. Now, f of something is 2 times that something minus 5. Okay, so that's up 2 times something minus 5. But the 5 is no longer x. Or sorry, the x is, let's say, it's not an x that goes here anymore. It's all g of x, which is 3x. Okay? So multiply this out. This would be 6x and then minus 5. So 6, on here. 6x minus 5. There you go. That's the answer. Okay. So that is f of g of x. Okay. Now what about domain and range? Okay. So domain, okay. Well, domain could be all real values or all real numbers. And I think the same is true for range. Okay? Like, so all real numbers. I don't see any restriction. I could go from negative infinity to infinity. I could plug in anything for x and I'll also get anything for y. Okay? Now that might change if you have some kind of parabola or some crazy looking polynomial. That might be different. But if it's just linear functions like this will tend to be the case. Okay, how about the other way around? What is g of f of x, also called g of f of x? Like that. Well, g of something is 3 times that something. So that's going to be 3 times something. Okay. But what that something is no longer x. It's actually this entire expression 2x minus 5. Okay. Now I need to distribute this 3. So that gives me 6x minus 15. Ooh, that's different from before. G of f of x. See, if I put these side by side, let's see. Uh, f of g of x turned out to be 6x minus 5. G of f of x ends up being 6x minus 15. Yeah, so expect to get different outcomes right, depending on which order you do these functions, right, which you plug together. Okay. I think domain and range, same thing as before. Domain, range, could be all real numbers because I don't see any reason for restricting any kind of restriction. We're not dividing, so don't have to worry about dividing by 0. There's no parabolas, so we don't have to worry about any like, local minimum or anything like that. All right, so moving on. Um, Example 6, movie theater charges $8.50 for each of the X tickets sold. A manager wants to determine how much the movie theater gets to keep on the ticket sales because they have to give the studio 75% of the money earned in ticket sales. Right? Yeah, so that's I don't know exactly the numbers forgot to in real life, but it's probably similar to this. Is that when you buy a movie ticket, a lot of that money is actually going back to the original studios. It's sort of like the movie theater sort of renting the movie to show, think of it that way. Okay. Okay, so they're allowed to keep K of X. So how much represents how much they're allowed to keep. So I would say let's say sales as a function of, or maybe revenue. How about that? Let's call it revenue. R is a function of S. So R for revenue could be $8.50 times the number of tickets. Number of tickets is X. Right? But what they're allowed to keep um, is 75%. Right? So, sorry, they have to give away 75%, which means they're allowed to keep the other 25%. That's it. Okay? If they have to give away 75% back to the studio, they're allowed to keep the other 25%. So it'd be 25% times number of sales. Right? And what we're looking for, what's going to make this a composite function, is I want the what they're allowed to keep as a function of the tickets that they sold. So something like this. Okay. And that would be 25% of something, but that something is actually the amount of money, which is $8.50 per ticket times the number of tickets. So put all this together. Let's see, what's 0.25 times 8.5? Okay, so put it all together. K of R of X. So what they're allowed to keep as a function of the revenue, as a function of the number of tickets, is $2.12 per ticket times the number of tickets sold. Okay? So this is it right here. That's also called K of R of X. Okay, they go that way. Okay. So from the theater's point of view, every time they sell a ticket, really what goes into their own pockets is about $2.12. If they sell 100 tickets, they just made $212. Yeah. And then everything else they have to return to the studio. Show the movie. Yeah. So composite functions. All right. Here, let's jump into these. So number 3. Okay, so all these here, they're looking for you to find the sum, the difference, multiplication, division for each of the. All right, so number 3, if f of x is x minus 2 and g of x is 2x minus 7. So f plus g of x is just f of x plus g of x, different notations for the same idea. We're just going to add these together. So add like terms. I got 3x here. I get negative 9 here. Boom, done. What's f minus g of x? That'd be f of x minus g of x. I'm going to have to subtract. So x minus 2x would leave me with negative x. Negative 2 minus negative 7. Here, negative 2 minus negative 7 is the same thing as negative 2 plus 7, which is 5. So it'd be plus 5. Boom, done. Okay. Now, if I want to multiply or divide, I think I'm going to have to be breaking out some FOIL right here. If I do f times g of x, which is f of x multiplied by g of x, okay? Keep in mind, this is not a composite function. This is just I'm multiplying the two functions. That's the same thing as x minus 2 multiplied by 2x minus 7. All right, it's FOIL time. First, outside, inside, last. So that's 2x squared minus 7x minus 4x, and then plus 14. We like that. Uh, Finally, well, they're going for f over g. If you did g over f, you would get a different outcome. So let's do f over g, just to stick to the book, of x, also called f of x over g of x. Okay. So f of x is my x minus 2. My g of x is 2x minus 7. Okay. And that does not simplify, so that's it right there. That's it. Boom, 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 boom. Just like that. All right, let's do next puzzle. Number 4, I have highlighted here. 4. So we get a new f of x and a new g of x. We've got x squared and x minus 5. Okay, so one of these looks like a parabola. It's interesting, maybe. So if you do f of x plus g of x, start with that. Well, there are no like terms, so we're just going to add everything up. Here's my f of x. Here's my g of x. Boom, done. That's it. To do f of x minus g of x. So start with my x squared, I'm subtracting off this x, and then minus a minus, this 5 turns back positive. Boom. Now that one's done. What if I do f of x times g of x? Okay. Well, I'm going to take this x squared and distribute it into each of these two terms. Distribute, which would give me x to the power of 3 minus 5x squared. Boom, done. And finally, if I do f of x divided by g of x, that would be x squared over x minus 5. Okay. By the way, that fraction does have a domain restriction, which is x cannot be equal to 5, because if you did plug in 5, you'd be divided by 0. So on a graph, this would show up as a vertical asymptote. Number 7, finance. Trayvon opens a checking account that he only uses to pay fixed bills, which are expenses that are the same each month, such as car loans or rent. Okay, so he's got this checking account. He's going to pay for the rent on his maybe his apartment every month and his car loan every month. Right, so instead money leaving the account. The checking account has initial balance of $1,750. Oh, and he is depositing $925 each month because maybe he's working a job and he's put some money into the account at the same time his bills are being pulled out of the account. Well, this is going to be a subtraction, isn't it? So the balance of the account can be modeled by A of x equals 1750 plus 925x. Okay, this is how much he's just putting into the account, right? Now, even at time 0, he already had 1750 in there when he opened it. He just immediately put that in, right? And then x is the number of months that have passed. So as he's working his job, he's always putting in $925 every month, right? Okay. So it's 10 months past, so you could add over $9,000 to the initial amount. But then his bills, so b is a function of x, bills is 840x. So there's this rent and this car loans, and so that's being subtracted. So define the function that represents the amount he has after he pays his bills. Right? So, well, that would be what he's putting in, a of x minus his bills that are being pulled out, b of x. Right? And I lined up the x terms. Right? So what's 925 minus 840 is 85. Right? So we started with $1,750. Right? This is a hard number of dollars. Right? Every month that passes on net, this account is gaining a little bit. It's gaining $85 per month, and then times number of months equals to, right? So we're looking at this function right here. Okay? And then they want you to graph this. Right? So, yeah, okay. And they give you this set of axes right here. So I'll make up my own axis. I'll show this from scratch. It's a skill that you guys should have too. Right? Be able to draw from scratch. Okay? Now, did they say during the first like 10 months or something? I feel like I said that somewhere. All right, well, their graph is only going up to 10, so they will do it too. Right? So x, which is the number of months, right? And then we'll say balance, which is in some number of dollars. Okay? So we'll go up to 10 here. Let's go 2, 4, 6, 8, 10. So 0, 2, 4, 6, 8, 10. And then put 1, 3, 5, 7, 9. Okay. You guys notice how I started this axis at 0 and then scaled it linearly? Okay. And I'm going to do the same thing for account balance. Now if I go up to 10 here, let me see how I should have scaled. What's 850 times 10 plus 1750? Because, sorry, that's 85. There, there. It goes up to 2,600. So maybe if I scale this up to 3,000, yeah, which is exactly what you both did. You went to 3,000. So 1,000, 2,000, yeah. So I'm starting at 0. Here's 1,000, and that's dollars. $2,000, $3,000. All right, so let's get some points here. I could always make an XY table and plug in some values, see what happens. So after X many months, what is well, I'll just call it f of x, right? Which could be this difference right here. Okay. Let's try month 0. Let's try month, how about 2, 5, 7, and 10? Okay. So okay, 1750 plus 85 times 0. That's 1750. How about what if I plug in 2? Getting 1920. How about if I plug in 5? I'm getting 2175. How about if I plug in 7? Getting 2345. How about if I plug in 10? 2,600. Okay. Right. Now, this equation looks linear. So I expect when I plot these 5 points, I could have plotted more, that they should all line up in a straight line. Okay. And that goes hand in hand with these axes starting at 0, 0 and being scaled linearly after that. Yeah. Right, so that's exactly how you want to draw your graphs. There might be a few weird exceptions to that, but pretty much the rule. So times 0 is 1750. Probably right about there. 2 months, got 1920. Right about there. 5 months, got 2175. That's probably right there. 7 months, got 2345. Right there. And 10 months, 2,600. Right there. Okay. Yeah, and what it's looking like is that all these points, yeah, they line up in a straight line. Yeah, they should, because it's a linear relationship. That's exactly it. You got it. Right, so you got a difference of functions. That's a good example there. Okay, 13. Find the composite f of g of x, g of f of x. State the domain and range for each. So 15 here. They've given us an f of x. Ooh, this is looking fancier. This is a whole parabola. Once you see x squared, you know that's the case. Okay. And then g of x could be x minus 6. Okay. So f of g of x could also write as f of g of x. Right. Well, what I'm going to do is take the whole g of x, which is this expression, and pop it in for the variable for f of x. So that's going to go right, something squared, but that something is not x anymore, it's x minus 6. And then this is also x minus 6. I'm just plugging in g of x over where an x used to be. And I saw this minus 2 on the end. Right, you guys see that? Right, here's my f of x. Something squared plus 6 times something minus 2. But something is no longer x. It's x minus 6, because that's g. Right? Now, I could boil this out. This is really, throwing the middle step here, guys. It's like this, right? Right, so I can clean this up. So I can go first, outside, inside, last, and then also distribute the 6. Don't forget that. Right? And then just clean this up and see what happens. Study x squared minus 6x minus 6x plus 36 plus 6x minus 36 minus 2. Right? And then this way, these x terms combine. So that would be, yeah, this is f of g of x is, I got an x squared. I got an overall of minus 6x minus 2. That'd be that. Right. How about domain and range? Domain and range. Right. Now, domain, I think, could be, here, I'll put it in interval notation, x such that x is an element of all real numbers. Right? Because I could plug in anything for x from negative to positive infinity. But I don't think that's going to be true for the range. Because look, for the range, I mean, this is a parabola, right? So it would bottom out somewhere. There would be some minimum y value. Okay? And what is that y value? Well, I can find with the vertex. You guys remember x vertex is going to be at negative b over 2a. You guys remember that? So in this context, my b is negative 6, so it's negative negative 6 over 2 times 1. I have this coefficient of 1 on the front. Okay. So it'd be 6 over 2 or 3. Now that's an x value. So what if I plug in 3 into this? So f of g of 3. You go that way. Okay. If I plug in 3 here, I get 9 minus 18. Let's try this out. 3 squared is 9. Minus 6 times 3 is 18. And then minus 2. That'd be negative 11. Right? Right. So here, just to give you guys a little picture, I know that at the coordinate 3, negative 11, this is not exactly a scale, but just get the idea. Okay? There's the vertex of a parabola that goes up like this. Okay? Now, the domain can be anything from negative to positive infinity, that's fine. But the range can only go down to negative 11. It's got to be something above that. It can't go below. So for the range, I'll say y such that y is greater than or equal to negative 11. Or if you wanted interval notation, you could write it as negative 11 to infinity. Okay. And I'll do it for domain also. Look like that. All right, so there you go. There's domain and range for that composite function. Now that's f of g of x. Let's try it the other way around. What is g of f of x? I bet we're going to get something different. All right, so I'm starting with the same two functions. I'll just have that there. And what is g of f of x? Also called g of f of x. Well, now I'm starting with my g function, which is something minus 6. But that something is f of x. It's this whole expression right here. X squared plus 6x minus 2. And then after the fact, I'm doing minus 6, because that's what g of something is that something minus 6. Okay. This one is just x squared plus 6x minus 8 is what that is. That's your g of f of x. Okay. Now, how about domain and range here? Now, I think the domain, same as it was before, it could be all real numbers. Right, so same notation as before. Here's set builder notation, here's interval notation, or here's kind of shorthand for you right there. But how about the range? Well, I'll do the same thing I did before. A little dot cloud over here. I know x vertex would happen at negative b over 2a. I remember that. It's part of the quadratic formula. You guys remember that? So in this case, that's negative at 6 over 2, which is negative 3. And then g of f of negative 3. I plug in negative 3 here. What do I get? So this comes negative 3 being squared is positive 9. So this is a 9 right here. Okay. Plus 6 times negative 3, and then minus 8. I'm looking at negative 17. Okay. So if I were to make a graph, I know here, x-axis, y-axis, if I go to negative 3, negative 17, there's a point right here. And this still a parabola that bends upward like that. Okay, this is not, again, exactly to scale. Okay. But there is a vertex at this point, and that tells me something about the range. Okay, so the domain could be anything, left or right, forever. Right? But the range, I can say y such that y is greater than or equal to negative 17. Or in interval notation, I could go bracket negative 17 to infinity plus parenthesis. So either way, that works. Okay, so there you go. Composite function. Number 18. A sporting goods store is offering a 20% discount on shoes. Mariana also has a $5 off coupon that can be applied with the purchase. She's planning to buy a pair of shoes that cost $89. Ooh, pretty pricey, but she has these two discounts. She has the 20% discount and also the $5 off coupon. Will the final price be lower if the discount is applied before the coupon or the coupon is applied before the discount? Ooh, well, how can we set up a mathematical framework to solve this? So I'm going to define discount as a function of x is, now it says 20% off. So you as the consumer, like put yourself in Mariana's shoes, maybe her old shoes, she's saying, I get to pay 80% of the listed price. Yeah. because 20% off, that means you pay 80%. So that's where that comes from. Okay, so you have to figure that out. Right? And then there's a coupon function. So coupon is a function of whatever price is that price minus $5. So the five in this context represents dollars. Okay. And she wants to use these in conjunction with each other. Now, should she take the discount and apply the coupon afterwards, or should she apply the coupon first and then take the discount? And it turns out that she'll pay slightly different amounts of money for the shoes, depending on which way she goes. And so discount, what if you do discount first, then coupon, right? Okay, and I'll do the opposite scenario later. So that would be like this. That'd be like taking the coupon of the discount as a function of x. Okay. So in terms of the order that happens, right, you see the price listed on the shelf. That's like x. That's the listed price. Then you take the discount after, so that's the discount first. After you do the discount, then you do the coupons. That'd be like this. Right. So that'd be something minus 5, but that something is the discount price. So it'd be 0.80x minus 5. So it'll be like that. Okay. And then what is the coupon of the discount of $89? Is $89 price? Well, let's just pop in an 89 there. Okay. So that'd be 0.80 times $89, and then subtract 5 after. That's zero point 0.8 times 89 minus 5. Okay. It's giving me $66.20. Okay, here, if I throw in a little dollar sign, okay, she would be paying that much. That's if she applies the discount first as a percentage and then the coupon afterwards. Now, what about the other way around? What if she goes coupon first, then takes the discount? How will that play out? Well, that's like taking the coupon value, like the coupon price function, right? And then take the discount on top of that. That's like d of c of x. Hey, see how this is different? C of d of x versus d of c of x. It's a little different, isn't it? Yeah. So what's that gonna be? Well, the discount is 80% of something. So 0.80 of something, but that something is not the price anymore. It's because if you apply the coupon first, it's the price minus, like the store price minus $5 because she already applied the coupon. Okay? Now you can clean this up by distributing the 0.80, right? So that'd be 0.80x minus, and 4/5 of 5 is 4. Huh. Look at that. Right? Actually, you can compare these directly at this point. So she goes discount first and coupon is this. Coupon first and discount is this. Okay? All right. Do you guys see how if she goes with the first plan, she actually saves an additional dollar? Yeah. Right. So you should I see why too. I see why. Because if she applies the coupon first and then discount, it's where that coupon itself gets discounted, so it doesn't count as much. Okay. So what is discount of coupon of $89 shoes? See what that be? If I plug in zero point 0.8 times 89 minus 4, okay, I should get, oh, it should be an additional dollar. Let's see. It is. It's $67.20. Like that. Okay. Yeah, so you want to take the discount first and then the hard number coupon after the fact. That will be the best deal. Right? Only by $1, but it's still a little bit better deal. All right. Okay, a few more with you guys here. All right. Ooh. Now, this set, they gave you 3 functions. They gave you a f of x, a g of x, and an h of x. Ooh. So f of x, we're calling 3x, so 3 times something. G of x, we're calling x plus 4. So that's something plus 4. And then h of x, we're going to do x squared minus 1. To graph that, it would be a parabola. So we're squaring something, subtracting 1. Okay. Okay, so 20. All right, so this applies to number 21 through 35. All right, and I got a couple highlighted that I want to do with you guys. Let's see, number 28. F of h of g of 1. Ooh, okay. I would prefer to think that is like f of h of g of 1. Right? Yeah, see how this was looking like Russian nesting dolls? Right, so maybe you could solve for g of 1 and then take h of that and then f of that.
Okay, so it's like one doll inside, so a small doll inside a medium doll inside a big doll. Okay. Or you could push this all together and solve this one giant master function. Maybe I'll try it both ways and see what happens. So f of something is three times that something. So three times what? Well, h of x is that something squared minus one. So something squared minus one, right? And g of x says that something plus four. So something plus four. Okay, so working inside out. Um, Here, actually, I have it in terms of x. So this is f of h of g of x. All right, we'll plug in one later. Okay? So the inside function is g of x. That's x plus 4. H of x says to square that value and subtract 1. So square that, subtract 1. Finally, the outside function says f of something. Well, that's just 3 times something. So the whole thing gets multiplied by 3. So go like this. Right? You could totally clean this up. Although this should be an acceptable form also. This kind of reminds me okay, maybe. That could be one way. Let's try f of h of g of 1. So now I actually need plugging 1. So I could plug it into this master composite equation, or I could go step by step by step. Let me try it both ways. I should get the same answer. So if I do 3 times, then here I got 1 plus 4 all being squared, and then minus 1. That's all multiplied by 3. Okay, I'm getting 72. So 72. Okay. Or what if I do g of 1? So 1 plus 4, which is 5. Right, so I got 5. H of that value, that's 5 squared minus 1, which is 24. And finally, f of something is times 3. So times 3, hey, it's still 72. Still 72. So whether you have a master composite equation or you go step by step by step, just one step at a time, either way, I'm getting 72. That's it. All right. 31. We got f of h of 0. Well, f of something, uh, here, actually, I'll just write here. Okay. So 31, f of h of 0. Okay. So f of something is 3 times that something. H of something is that something squared minus 1. Okay. So this would be f of h of x. It could be like that. Okay. Uh, if you like, you could expand this out as 3x squared minus 3. Yeah, could do that. Okay. Now, what is f of h of 1? Well, where the x is, I can put a 1 now. So it's 3 times 1 squared minus 3. There's 3. I think it'd be 0, right? It'd be 0, right? Or if I break it down step by step, like what is h of 1? Well, if I plug in 1 here, that's 1 squared minus 1, which is itself a 0. And then f of something is 3 times that. 3 times 0 is still 0. Yeah, so it's the same thing. So okay. All right, I'm gonna do one more with you guys. Last one for the win. Number 37, volume. Right now, this one I really like a lot. We got the volume of a weather balloon as a function of its radius r is 4/3 pi r cubed, which is the volume of a sphere. So go ahead and draw you guys a picture. So here's a big old weather balloon. And we're gonna pump this weather balloon, but save that for later. Okay, so we got this pump hooked up to it. Right. Okay. And so imagine 3D. This is a big old sphere with some radius I'm calling r. And the volume of that balloon as a function of its radius, since it's basically a sphere, is 4/3 pi r to the power 3. Volume of the sphere. Okay, so that's all fine. Good, right? Right. But there's another detail here. The balloon is being inflated so that the radius is increasing at a constant rate. So here's our pump. You know, like this big balloon is increasing. And the radius as a function of time is 1/2 t plus 2, right? Where t is the number of seconds, so number of seconds that have passed, and 2 is the number of meters. Right? So at time 0, before we hit the pump at all, there was some volume in the balloon, and there was a radius of 2 meters, right? So it was already at 2 meters, and now starting at time 0, now right. Now, here's a total side thought, but I think it would be more realistic to have the volume change at some constant rate, right? Because maybe we're pumping in some constant volume, and then the radius grows slower and slower and slower as time passes, although that's mathematically more complicated. So they gave you the mathematically easier one, which is what if this radius was growing at a constant rate? Okay. Yeah, less realistic, but easier to work with. And what they want to find is What's the volume? Not as a function of radius, but as a function of time. So we want to know what is volume as a function of time, right? So after say like 5 seconds have passed, how big is this balloon, like in terms of volume, right? Well, you can get that by creating a composite function. Spell that out. Composite function, right? V of t is the same thing as v is a function of r is a function of t. So we can go like that. So let's do it. So volume is, now I know it's 4/3 pi times the radius cubed, so I'll start plugging that in. 4/3 pi, right, times the radius cubed. But in place of radius, now I know the radius is a function of time, how many seconds have passed, which is 1/2 times the number of seconds, and then plus 2, because at time 0 started out with 2 meters radius. Okay. So I got this. Actually, right. Yeah, that'd be a pretty good volume expression there. Right? Now, if you want to expand this out, you totally could. It would take some time because watch it. It's to the power of 3. We got a binomial to the power of 3. You guys remember Pascal's triangle? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. Okay. So you can play out this row right here to do this binomial expansion. So be this first term to the power of 3 plus then this first term squared times this 2, but all with a coefficient of 3 on the front, and then this term times the 2 squared, also with the coefficient of 3, and then just the 2 to the power of 3. All right, okay. And that would be furthermore multiplied by 4/3 pi. So here what I'm going to do, number 37, is pull this out of the book. So I'm reading off the teacher's guide, which is off screen. It says volume. This is a function of time. They went ahead and expanded it out. And they're saying it's pi over 6t to the 3 plus 2 pi t squared plus 8 pi t plus 32 over 3 pi. Okay. Okay. So that should also work, right? If you go through all the expansion. Now find the volume of the balloon after 12 seconds. So what's V of 12? Okay. Now I should, of course, get the same value whether I use mine or I use the answer from the book because these should be the same thing. So let's try that out. So let's go 4/3 times pi. All right, 4/3 pi. And then in parentheses, I got 0.5 t. And t, I'm going to put 12. Right, 12 seconds, right? Plus the 2 meters that was originally, and then all to the power of 3. Okay. So I'm getting 2145 cubic meters. You get these all the meters and cubic meters. I said that. Right? Now, what if I plug in the value from the book? So it's like pi over 6. Again, I'm looking for it to be the same answer. Let's see it, right? Times 12 to the 3 right here. Right? Plus 2 pi times 12 squared plus 8 pi times 12 plus 32/3 pi. Okay. Come on, same number. Oh yeah, it is. Ding, 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 ding. So there you go. There's volume as a function of time, which we got by making a composite function. Volume is a function of radius, and then radius is a function of time. Just embed one function in the other. Boom. We got the answer. And that is a wrap on 6-1.